So what we've been building up to is being able to solve a linear first order differential equation of the form dy by dx plus p times y is equal to q, where p and q are functions of x. So I've just abbreviated it so that I don't have to keep on writing up p of x and q of x. Okay, so p and q instead. They're not constants, they are functions of x. Okay? Now, what we've done in the examples is built up to saying, okay, well, I can solve these differential equations if I can get the left-hand side, so left-hand side of the equation here, into the form of a perfect derivative. And I can do that by multiplying by some function of x. Let's call that function of x r. So I'm going to introduce r as some function of x, and this is what we refer to as the integrating factor. So I'm going to multiply through my differential equation by r. So I would get r times dy by dx plus rpy is equal to rq. Okay? Now I want this left-hand side to be a perfect derivative. So I want this to be d by dx of r times y. Okay, that's what I want that left-hand side to be. Then, once I've got it to that form, I can integrate. So, let's take a look at d by dx of r times y. Well, that would be, using the product rule, r times the derivative of y, so r dy by dx, plus y times the derivative of r, so dr by dx times y. And I want this to be precisely the same as this. Okay? Now clearly for this equation I can get rid of the r dy by dx's. They're gone. So I now have dr by dx y is equal to rpy. I could divide both sides by y, okay, where y is non-zero, so y not equal to 0, so dr by dx is now equal to r times p. Okay, right. So now what I've ended up with here is a first order differential equation that is separable. So we can use A-level maths techniques to solve that. So let's go up here. So we've got dr by dx is equal to r times p. So I'm going to separate the variables. I'm going to get the r's on the left-hand side and everything else on the right-hand side. So I'm going to divide both sides by r and multiply both sides by dx. And I'm going to integrate both sides. So the left-hand side integrates to the natural log of r. Okay, well, I'll put modular signs around it, can't I? And then the right-hand side integrates to, well, I'm just going to leave it like as the integral of p dx. Now the reason why I'm going to leave it like that is because, remember, p is not a constant. This isn't p times x plus some constant of c. P is actually a function of x. So this could be cosine of x, for example. Don't know. Okay? So don't think that this is mistakenly a constant. So now to find r, well, I can write that as r is equal to e to the integral of p dx. And here is my integrating factor. So if I get my differential equation into this form, I can find the integrating factor by finding e to the integral of the coefficient of y dx. Once I've found that, I can multiply through my equation and get it into a perfect derivative form. Okay? That is how we use the integrating factor.